the second thing that I want to highlight before I go into the general discussion is the properties of solids, liquids and gases. That would be 3.2.3. So explain the physical differences between solids, liquids and gases. So if you turn to page yeah, if you turn to page 10 of your notes, there's basically a table which summarizes all these. Okay, so you can talk about all the shape, volume, compressibility, and the student should actually be familiar with this stuff from IGCSE. But one of the things that you need to highlight is the mean molecular separation. So in solids, if the mean molecular separation is approximately, let's say R, okay? In liquids, also the mean molecular separation is pretty much there. It's pretty much R also, okay? Only thing is that these clumps of molecules are free to move about. In gases, however, the mean molecular separation is much higher. It's about approximately 10 R, right? That is summarized here in the table also. So this thing is going to play an important role in explaining one of the features of latent heat. Okay, so we'll move on to the general discussion of this section. So if I have a graph of temperature in degrees Celsius versus time in seconds, okay, and I'm supplying energy at a constant rate. Okay, I have a block of ice, okay, of mass m, okay, and I start off at -5 degrees Celsius, alright? So at -5 degrees Celsius, I'm supplying energy at a constant rate. What's going to happen is that as time passes, the temperature is going to increase steadily, okay, until I reach 0 degrees Celsius. At 0 degrees Celsius, the temperature is going to remain constant for a while my block of ice melts, okay. When all the ice has melted, the temperature is going to increase steadily again to a point where the temperature is now 100 degrees Celsius, alright. At this point again, the temperature is going to remain constant while the water boils. When all of the water has boiled, then if I continue to add heat to the steam, then the temperature of the steam will go on increasing. Okay, so what's happening in each of these steps? The first step here, I'm supplying heat. What's happening is that I'm increasing the internal energy. Of course, if I'm supplying heat, it has to increase the internal energy of the system. Over here, the heat that I'm supplying is going into increasing the average random KE. Okay? It's increasing the average random KE. Okay, the potential energy pretty much remains constant. Why? Because potential energy is concerned with the state of the object, right? So over here it stays in a solid state. It's increasing the average random KE. How do I calculate for this portion the heat that I've supplied? The heat supplied will be, like we just mentioned, the mass multiplied by the specific heat capacity of ice. Okay, that's very important because when we're talking about ice, we'll see the specific heat capacity of ice multiplied by the change in temperature. In this case, it will be 5 degrees Celsius. Okay. Over here, what's happening is the average random KE stays the same. Okay, so the heat that I'm adding goes on to increases the potential energy. Okay, why? Because the heat that I'm supplying is breaking the bonds between the solid molecules, right? So it increases the potential energy, and the heat that I supply can be calculated with this formula here. The mass times the specific latent heat of fusion of water or ice. Okay, it's the same thing. Latent heat of fusion is basically the amount of heat required per unit mass of ice to melt it at 0 degrees Celsius. So the amount of heat required to melt a substance or change the state of a substance at a constant temperature is called the specific heat. It's called the specific latent heat. And since we are talking about change of state from solid to liquid, we will be talking about latent heat of fusion. Make sure that you're using latent heat of fusion here in between a solid state and a liquid state. Okay, whether it's changing from a solid to a liquid or liquid to solid is immaterial. You will still use specific latent heat of fusion. Okay, now that will help you to calculate the heat supplied in this portion. In this portion here, what's happening is something similar to that portion there. The average random KE goes on increasing, and the heat supplied can now be calculated using the mass multiplied by the specific latent heat of water, because now we are in a liquid state. Water multiplied with the change in temperature. Okay? And over here again we have an increase in potential energy. Okay? And the heat supplied can be calculated using mass times latent heat of vaporization now. Okay? So latent heat of vaporization is the amount of heat required to convert a unit mass of a liquid to a gas or a gas to a liquid. Alright? Now notice that the latent heat of fusion is going to be lesser than the latent heat of vaporization always. Why? This is related to the mean molecular separation that we were just talking about. In going from a solid to a liquid, the mean molecular separation remains approximately the same. So I have to put in only so much energy in order to change it from a solid to a liquid. Okay? But in going from a liquid to a gas, I have to not only break the intermolecular bonds, but I have to increase the intermolecular separation to about 10 times of what it was originally. So I need to supply a lot more energy, and that is why the latent heat of vaporization will always be larger than that of fusion. Okay, so this pretty much sums up everything in this portion, and you want to go step by step and make sure that the students understand that any kind of a problem related to specific latent heat or specific heat capacity should be broken down into steps like this, and each step needs to be calculated and then added up separately. So this kind of a graph is going to help them not only understand but also solve their problems in the exam. So yeah, that's a summary of the second part.